Let's prove that 5 minus square root of 3 over 2 is both irrational and algebraic. And then I'll repeat for this second number, square root of 3 minus 2 square root of 5. First off, we observe that 5 is rational and square root of 3 is not rational. And so therefore the difference, 5 minus square root of 3, must be irrational. Okay, that's by one of the other theorems in this section. So if 5 minus square root of 3 is irrational, and I divide by a rational number, 2, then that means that the quotient, 5 minus the square root of 3 divided by 2, must also be irrational. So that's the proof that 5 minus square root of 3 over 2 is irrational. To show that it's algebraic, I need to construct a polynomial so that if x is equal to 5 minus the square root of 3 over 2, then if I plug in x, I get 0. To do this, I'll basically get rid of the square root. So if I multiply by 2, I get 2x is equal to 5 minus the square root of 3. Now let me subtract 5. And then square both sides. So I get 4x squared minus 20x plus 25 is equal to 3. And so subtracting, we get 4x squared minus 20x plus 22 is equal to 0. So there is my polynomial. So let f of x be equal to the thing that we just got, 4x squared minus 20x plus 22. Then if I plug in 5 minus square root of 3 over 2, I will get 0. I could have divided by 2, make it 2x squared minus 10x plus 11. That would also work. Let's now show that if we have alpha equals square root of 3 minus 2 square root of 5, that this is also irrational and algebraic. For this problem, it's actually easiest to first show that it's algebraic. So first thing, we're going to have to square twice to get rid of all the square roots. So if I have alpha plus 2 square root of 5 equals square root of 3, then if I square, I get alpha squared plus 4 times the square root of 5 times alpha plus the square of 2 square root of 5, which is 4 times 5 for 20, equals 3. Now let me get the one remaining square root on the right side of the equation. So I have negative 4 square root of 5 times alpha. And bringing the 3 on the other side, we get alpha squared plus 17. So squaring again, we get that alpha squared plus 34 alpha, alpha to the fourth, pardon me, alpha to the fourth plus 34 alpha squared plus 289 is equal to the square of 4 square root of 5 is 16 times 5 is 80, so 80 alpha squared. And so finally, getting everything over to one side, we get alpha to the fourth minus 34 minus 80 is 46. Alpha squared plus 289 equals 0. So our function is going to be f of x is equal to x to the fourth minus 46x squared plus 289. So that proves that the number is algebraic because I now have a polynomial with integer coefficients, degree 4, so that when I plug in square root of 3 minus 2 square root of 5, I get 0. Now, how do I tell if it's irrational? Well, I can't just simply say square root of 3 minus 2 square root of 5 must be irrational, because an irrational number minus an irrational number might turn out to be rational. So the way that I will prove that this number is irrational, let me take a look at the possible rational roots. And the possible rational roots will be things in the numerator that go into 289. In our case, there are only three possibilities: plus or minus 1, plus or minus 17, and plus or minus 289, divided by plus or minus 1. So there are 6 possible rational roots: plus or minus 1, plus or minus 17, and plus or minus 289. And now we can quickly check to ensure that none of those things are actually roots of the polynomial. So let me actually do this fairly quickly. So 1 to the 4th minus 46 times 1 squared plus 289. That's not equal to 0. If I take 17 to the 4th minus 46 times 17 squared plus 289, I don't get 0. And if I take 289 to the 4th minus 46 times 289 squared plus 289, again, I don't get 0. I get something quite large. That's the positive ones. The negative ones will also work out in much the same way. So none are roots. So these are the only possible rational roots. None of them work, which means that the only roots that do exist must be irrational. So the root alpha is irrational. And so that's a way that the rational root test can be used to check that a number is irrational.